Hello everyone and welcome to Chapter 4, Stoichiometry of Chemical Equations. We're going to start off here talking about chemical equations just in general, and we're going to get into balancing chemical equations, which is the first step of this chapter here. So, if you remember from previous chapters, chemical equations tell us what is involved in a chemical reaction. It shows this is going to react with this to create this, in a nutshell. But what also is included in these chemical equations is not just what is present. Chemical equations also tell us how much of each of those things are present. And that is actually just as important as what is present. If all you know are the molecules that are reacting, you only have half the picture. The other half is how many of those things are going to react, and then how many of the product molecules are going to be made. So if you remember, subscripts tell us the number of atoms within a compound. So the 2 here, for example, that is the number of oxygen atoms in the oxygen molecule. Same thing here. We have 2 hydrogens in water. So subscripts tell us the number of atoms within a compound. Coefficients, which are the numbers out in front, those tell us how many of the entire molecule or atom we have in the chemical reaction. So here, H2, if you remember, that's one of those weird ones. That's one of the 7 diatomic elements, so you could kind of think of it as both a molecule and an atom, since it is the free elemental form of hydrogen. So we have 2 H2s that are participating in this reaction. If there's no coefficient given here, then it's understood to just be 1. You'll never see a 1 out in front here. If there is just 1, then you just leave it blank and it's understood to be 1. And then we have 2 waters. So we are told not just what's present, but also how much of each of those things are present. So in that particular chemical reaction we saw there, if we wanted to read the chemical equation like a sentence, we could say 2 molecules of H2 react with 1 molecule of O2 to produce 2 molecules of H2O. Now notice there that we're talking about numbers of particles. We are not talking about masses, because when reactions take place, it is what's actually literally occurring are little particles bumping into each other and reacting with one another. So this is a particle-to-particle interaction. It's not take this mass of this thing and react it with this mass of this other thing, and it comes together. It's a particle-to-particle interaction. So we're talking about particles here, not masses. Now we could then take those particles and relate it to the mass, but that would be a whole extra step. We don't do we don't make the comparison based on the masses. We make the comparison based on the actual numbers of particles, and then if we want to find the masses, we can do that as an extra step later on. Alright, so when we're looking at these chemical reactions, one of the things that is really important when we're analyzing these and when we're writing these for ourselves is these chemical reactions have to be balanced. And what I mean by that is the number of particles and the type of particles on each side of the reaction arrow. This is the technical term is the reaction coordinate, but that's kind of a it's not used quite as often. Essentially, it's just the arrow here separating the reactants from the products. The stuff that we have on the reactant side needs to be exactly the same as the stuff on the product side, just rearranged, essentially. But the number and type of particles must be the same on both sides. If they are not the same on both sides, what that means is, number one, you have an incorrect chemical reaction. But the reason that you know that is because if you have different numbers or types of atoms on the 2 sides of the reaction, you are breaking the law of the conservation of mass. You can't start off with 4 hydrogens on the left and end up with 5 hydrogens in your product. Where did the extra hydrogen come from? Who knows? It just poofed out of nowhere. That doesn't work that way. Science does not work that way. Whatever you start with, you're going to have that at the end as well. It's just going to be rearranged. They're going to be bonded together differently. But you can't create or destroy mass. So, we have a few examples here that we're going to work through for balancing chemical equations. When we're balancing these to get the same number of atoms on both sides and the same kind of atoms on both sides, the only thing we are going to change is the coefficient. We are not allowed to change the subscript, because if we change the subscript, then we've actually changed the molecule itself. So if I were to say, I don't want SO2, I want SO3, it's not allowed. That would be an entirely different molecule, which would make this an entirely different chemical reaction. We're not allowed to actually change the molecules. We're only changing the number of them that are participating, and that is allowed. So for example here, we have SiO2 reacts with carbon to form SiC and CO. So if I look at what I have so far, I have 1 silicon on the left, 1 silicon on the right. So that is balanced. I have 2 oxygens on the left, only 1 oxygen on the right. And then I have 1 carbon on the left and 2 carbons on the right. So to get everything to balance here, what I'm going to do is I'm just going to play around with these coefficients until it is balanced. So I'm just going to pick one of the unbalanced elements and see if I can balance that. So I'm going to do oxygen. I have 2 oxygens on the left, only 1 on the right. So I'm going to put 2 here to get myself 2 oxygens on each side. So I have 2 oxygens here, 2 oxygens there, because I have 2 of this entire thing. So my oxygen is now balanced, but now I've made the carbon even less balanced than it was. It wasn't balanced to start off with, but it's now even less balanced, because I have 1 carbon on the left and 3 carbons on the right. Thankfully, there's a really easy way to fix this, because here we have just carbon all by itself. And so we can do 3 of those, and now we have a balanced chemical equation. 1 silicon, 1 silicon, 2 oxygens, 2 oxygens, 3 carbons, 3 carbons. So why don't you go ahead and give this next one here a shot. Go ahead and pause the video, see if you can work out a way to balance this chemical equation here. Again, only using coefficients. Let's go ahead and pause the video now. Alright, I hope you gave that problem a try. Let's go ahead and take a look at it together. So when I'm working through these, and I know I didn't do that here in the first one, but that was just because it was a relatively simple one. But from here on out, I will be doing the problems in this way. When I'm doing these, I actually like to write down what I have on each side, just to kind of keep track of what I have. So on the left side of this equation, I have sulfur, hydrogen, sodium, and oxygen. And I should have the same things on this side, and if I check, I do have sodium, hydrogen, or sorry, sulfur, hydrogen, sodium, and oxygen. And on the left side, I have 1 sulfur, 3 hydrogens, 1 sodium, and 1 oxygen. And on the right side, I have, let's see, 1 sodium, 2 hydrogens, 2 sodiums, and 1 oxygen. So, as it sits right now, my sulfur is already balanced, my oxygen is already balanced, but my hydrogen and my sodiums are not. So I'm going to pick one of these to balance first. And as a general rule of thumb, if you have a choice between multiple things that are unbalanced, it's generally a good idea to do the stuff other than hydrogen and oxygen first. Now, I say it's just generally good because there are some situations where it actually won't end up being easier, but more often than not, if you balance the stuff other than hydrogen and oxygen, it'll end up being a little bit easier for you. So we're going to go ahead and give that a shot here. So if we're going to balance the sodium first, to do that, we would need to have a 2 here, and sorry for not giving myself any space to write that in there, but we put a 2 in front of the sodium hydroxide because this is our only source of sodium on the left side of the reaction. So if we do that, this now becomes 2, but we're also now going to have 2 oxygens and 4 hydrogens, because putting that 2 in didn't just affect the sodium, it affected the whole molecule, and so we get twice the number of everything in that molecule. But that's fairly easy to fix. The effects of that are fairly easy to fix, because if you notice here, the oxygen, which was balanced before, is now not balanced. The hydrogen, which was not balanced before, is even more unbalanced, but it's an easy fix, because if we put a 2 in front of the water over here, now it's balanced. So 2 in front of the sodium hydroxide and a 2 in front of the water gives you a balanced chemical equation. Alright, let's do another one of these together, because I believe there's some more examples here in the next slide. So I'll let you do some of those on your own, but for this one, let's go ahead and do this one together. So this one is a little bit simpler in that there's only 3 things, 3 different elements: carbon, hydrogen, and oxygen on both sides. If we look at what we have, initially we have 3 carbons, 8 hydrogens, 2 oxygens on the left, 1 carbon, 2 hydrogens, and 3 oxygens on the right. So, again, taking my general rule of thumb here, it's better to balance the non-hydrogen and oxygen stuff first. So to get the carbon to balance, we would put a 3 in front of the CO2. And again, I wish I'd given myself extra space there, but oh well. So 3 CO2 gives me 3 carbons. And it also is going to change the number of oxygens. So I had 3 before, but now I have 3 times 2, which is 6, plus another 1, which gives me 7. Alright, so we balanced the carbon, but we made the oxygen even more imbalanced. But that's okay, we'll deal with that later. So now let's balance the hydrogens. Just because right now anyway, there's no way for us to balance those oxygens. Because we can only, so we have more oxygens on the right than we have on the left, but increasing the oxygens on the left can only happen by values of 2. We can only get orders of 2 on the left. So there's no way for us to balance the oxygen by just putting integer values in front of the oxygen here. So let's go ahead and balance the hydrogen first and see what happens. So we have 8 hydrogens on the left. We have 2 hydrogens on the right. So if I want to get those to balance, I would need to put a 4 in front of the water. This is my only source for hydrogen on the right side. So to get 8 hydrogens, I would need 4 of these. But again, that's also going to affect my oxygens. So now I have 10 oxygens. 6 from here, 4 from here. That gives me 10. And now I can balance those oxygens, because now I have a multiple of 2 in the number of oxygens on the right side, and I can get that with a 5 in front of the O2. So if you had tried, after balancing the carbons, to get the oxygen to balance, you would have had a tough time of it. You would have worked at it for a while, and maybe eventually you could have gotten there. But in that case, it was easier to go ahead and try to balance the hydrogen first, because then balancing the hydrogen actually ended up making the oxygen balance easier. All right, I think we have one more page here of examples to work through. So why don't you try the first two on your own, and then we will talk about the second two and work through the second two together. But go ahead and I'll go ahead and give you the answer for the first two as well. But go ahead and try to solve those first two on your own. So go ahead and pause the video now. Okay, so with this first one here, hopefully, when you work through it, you realized that there was no way to get this thing to balance with only one of this. If you notice here, we can only get oxygens in groups of 3 on the left. We can only get oxygen in groups of 2 on the right. And so what you should have ended up with is having 2 of these and 3 of those to get your oxygens to balance. And then now, because you have extra potassium and chlorines, you need the 2 in front of the KCl. And so now we have 2 potassiums, 2 chlorines, 6 oxygens, and 6 oxygens. All right, and again, just because I'm expecting you to have gone through and actually worked out all these on your own, I'm not doing the whole process for these first two. Just explaining how you would have gotten the answer. So this second one here is actually, I think, probably the easiest one, the easiest one out of all the ones that we're looking at. So if you notice here, we have 1 calcium, 2 sodiums, 1 sodium, 1 carbon, 3 oxygens, 3 oxygens. And so all you needed was, boop, just that, a 2 in front of the sodiums, and it's done. No other fancy stuff needed. Okay, so then moving on to these last two here. So this is another combustion reaction, similar to the one we did back here. This was the burning of propane. So if you like to grill, you have a propane grill, this is the chemical reaction that is actually occurring when you burn the propane. This is a similar chemical reaction here, but not with propane. This is, I think, some kind of sugar. But regardless, we have some combustion happening here. I'm going to go ahead and write these up higher just because I'm going to need the space for this bottom one. So I have carbon, hydrogen, and oxygen on both sides. I start with 5 carbons, 10 hydrogens, and 3 oxygens on the left, 1 carbon, 2 hydrogens, and 3 oxygens on the right. So my oxygens actually start balanced, but I'm betting it's not going to stay that way. If I balance the carbons first, I need to put a 5 in front of that CO2. So now I have my carbons balanced, but now I've thrown my oxygens way out of whack. So they were balanced, but now I have 10 from the oxygens here, and then another one, which gives me 11. Again, I'm hesitant to balance the oxygen first here. You could try that, and it might... No, you wouldn't be. That wouldn't end up working that way. So the main reason why I would caution you to try to balance the oxygen first here is because everything in this whole reaction has oxygen in it. This has oxygen, that has oxygen, this has oxygen, that has oxygen. Everything has oxygen in it, whereas the hydrogen only shows up in one place on both sides. So not only is it a good rule of thumb to leave the hydrogen and oxygen for last, but also if you have something that only shows up in one place on each side, you generally want to try and work those out before you do something that shows up everywhere. Because what will end up happening is if you balance the thing that shows up everywhere first, then when you go about trying to balance the other parts, well, now you just messed up that one too, because it's everywhere else. So any changes you make to anything else is going to throw that the oxygen out of whack. So let's do the hydrogen first here. So we have 10 and 2, so we need 10 on the right. The only way to get that is with a 5 in front of the water. So that gets us 10 hydrogens, but that also is going to increase the number of oxygens we have. So we have 10 from here, and then 5 from here, which gives us 15. Now we can balance the oxygen. We have 3 right now. We don't want to try and get the oxygen balanced by putting something in front of this molecule, because if we change the number of this molecule, we're going to change the carbons and the hydrogens. But we can put something in front of this, and the only thing that's going to change is the oxygen. And if we put a 7 in front of it, that would give us 14 oxygens from this, and then we have 1 from there, and voila, 15. So we have our balanced chemical equation. So then the last one here, I want to point out kind of a little trick that you can do. It's not really a trick. It's just I almost call it a shortcut. It kind of is a shortcut. If you notice here, we have sulfate and sulfate. Technically speaking, we could do the same thing with hydroxide here, but the hydroxide kind of gets lost in the water, and so I'm not going to do that with the hydroxide, but it technically does work with hydroxide too. We're just not going to do that here. But the sulfate, we have sulfate here on the left, we have sulfate on the right. The sulfate doesn't actually change. What it's bonded to changes. So it's in a different place. It's connected to different things on each side of the chemical equation, but the sulfate itself doesn't change. And so for reactions like this, where we have polyatomic ions that are not changing from one side of the reaction to the other, we actually don't need to split that ion up. We can leave it as a complete ion. So in the case of this problem here, we would have aluminum, oxygen, hydrogen, and sulfate on both sides of the chemical reaction. So if we look here, we have 1 aluminum, we have, let's see, 3 oxygens that are not in the sulfate, because remember, we're not counting those. This is part of the sulfate. We have 1 sulfate on the left side of the chemical reaction. And then outside of the sulfate, which I guess the sulfate doesn't have hydrogen anyway, but we have 3 plus 2, which is 5 hydrogens. On the right side of the equation, we have 2 aluminums. Outside of sulfate, there's only 1 oxygen. There are 2 hydrogens and 3 sulfates. So we can kind of pick which one we want to balance here first. We could go for the aluminum or the sulfate. I'm going to go ahead and do the aluminum first. I don't really think it'll matter either way, but the aluminum can be balanced by putting a 2 here. We had 2 on the right, put a 2 there, that gives us 2 on the left. It's going to change our oxygen and hydrogen as well. So now we're going to have 6 oxygens, and let's see, so yeah, that'd be 6 plus 2 is 8 of those. And I'm going to balance the sulfate next. So I have just one sulfate on the left, 3 on the right. So to get that to be balanced, I need 3 here. Again, that's going to change our hydrogens. So we had 8 before, but now we have 6 here, 6 here, which gives us 12. So my aluminum is balanced, sulfate is balanced. So then the last thing I need to do is to balance the oxygen and hydrogen, which is easy enough to do with a 6 in front of this water, which gives me 6 and, oops, not 8, 12 hydrogens. 6 times 2 is 12, 6 times 1 is 6. And so there we go. 2, 3, 1, and 6 are the coefficients for that particular reaction. All right. I know this was a little bit of a long video, but I decided I wanted to keep all of the balancing stuff into one video all by itself. So in the next video, we will start looking at different kinds of chemical reactions. So we're going to look at several different kinds of chemical reactions, not all in the same video, thankfully. We're going to look at precipitation reactions next. Then we'll look at acid-base reactions, and then redox reactions. And then we will finish up the chapter with some stoichiometry. So we will pick up next time with the precipitation reactions.